Greetings! Welcome to Electronics 2. This is lecture number 23 and I am Razavi. Today we will continue to look at the frequency response of other types of circuits, in particular the common base and common gate topologies. Last time and previous times we looked at the frequency response of the common emitter and common source amplifiers, and we built up some fundamentals there. Now we can extend those ideas and those skills to the analysis of these other stages. So today we will first look at some examples of high-speed circuits, just so that we see what applications there are for these types of studies that we are doing in this course. And then we will go into the analysis of the common base and common gate stages. All right, before we go there though, let's just take a look at what we covered in the previous lecture. We talked about the dominant pole approximation as a useful approximation in many different cases. And we said that if the denominator of the transfer function can be written in this form, as squared plus bs plus 1, so there's a 1 here for the constant value, and if we know that one of the roots is much less than the other root, so omega p1 is much less than omega p2, then it turns out that the lower pole frequency, the dominant pole frequency, is given by the inverse of the S coefficient, so that would be approximately 1 over b. So that's a quick way to determine the dominant pole from the denominator of the transfer function. Of course, we can always solve this quadratic, not a big deal, but this gives us a nice simple expression that will show the trade-offs in the design and what precautions we need to take before we start the design process. Okay, we also saw that there are some fundamental trade-offs when we talk about amplifiers. In a simple example, using a common emitter stage, we saw that we ended up with a trade-off between the speed, meaning the bandwidth of the circuit, the gain of the circuit, and the power dissipation. And this is something that we encounter in all circuits. So nothing is free. So if we want to have a lot of bandwidth, we have to compromise the gain or the power consumption. And that's important to remember in circuits that we will follow. All right. So today we start with some examples from real life to see what kind of frequencies people are dealing with, what kind of challenges we face when we want to push the speed of circuits. So I'm going to go to the International Solid-State Circuits Conference again, ISSCC. I showed you some papers from here a few lectures ago, so I will go there again. This is from 2018, and we look at a few papers there to see what kind of speeds they are looking for and why. So here's an example. In fact, I showed you this example last time, but I was just showing you the use of these cascade circuits that they have here as amplifying stages. But let's look at the title of the paper. It says it's a 60 gigahertz transceiver, right? Don't worry about all the other stuff. It's the 60 gigahertz transceiver, wireless transceiver that operates with a carrier frequency of 60 gigahertz. Now, 60 gigahertz is a very high number. It's a very difficult frequency to work at. But you can see that they have these transceivers, radio transceivers, that operate at these frequencies. Now, why do I need to go to 60 gigahertz? We saw that Bluetooth operates at 2.4 gigahertz, Wi-Fi at 2.4 and 5 gigahertz. So why do we need to go to 60 gigahertz? Well, the motivation is that at this frequency, we can transport much more data. For example, you want to download videos wirelessly from one device to another device, and the video is, for example, high definition video, so the data rate is very high, and that's not something that we can easily perform using Wi-Fi or Bluetooth, so we go to these frequencies. And there are a number of applications for this, so here are two cases. So for example, you want to have a connection between a home and some sort of base station, some sort of tower with a very high data rate for this transport. So the 60 gigahertz link would be useful here. Another interesting application that people are thinking about is actually in virtual reality, because here also we are dealing with massive amounts of data that have to travel between the headset and the base. So the data rate is very high, and this is preferably a wireless connection so that you're not connected, you're not tethered to the base as you move around. So for this wireless connection, we need a high speed data link, and the 60 gigahertz band would be a good candidate. So that's one example. Another example, again from the ISSCC, is this paper from IBM, from Intel. This reads a 112 gigabit per second transmitter, right? Don't worry about the rest of the stuff. So this means that this transmitter can transmit 112 billion bits per second, right? It's a very high data rate. Just to give you an idea, in Bluetooth, the data rate that we can support is about 1 megabit per second, right? This is 112 gigabits per second. So it's a very high data rate. And I just copied the circuit from one of their figures, and you can see something familiar here, right? We can see that there's a differential pair, which they call the driver, with a current source here. And this differential pair drives something which is actually the output of the transmitter. So at least we see some familiar circuits in what they have done. And this output has to run at such a high rate, 112 gigabits per second, and that becomes extremely challenging to design. Now, what is this anyway, such a high data rate transmitter? Where do we use this? Well, here's an example. Suppose that you have a PC board inside your computer, and there are two chips, and these two chips need to talk to each other at a very high data rate, right? For example, a processor and a memory or something. So when we go through this PC board, there's a trace that goes from here to here. That trace has many imperfections. And due to those imperfections, the data is corrupted. The data is distorted. So we need to have proper design for transmitting this data from here to here, and then for receiving it. And that becomes an interesting challenge. Another example are data centers, as you can see down here. Here's a data center. You have all these racks of various servers, computers, right? And these all have to be connected to each other. Usually they're connected from the back with lots of cables and lots of maybe optical fibers. So we need to be able to transport data at these speeds, 50 gigabits per second, 100 gigabits per second from here to here. And if you pass it through a cable, that cable has many imperfections. So that becomes a challenge. How do I transmit such a high data rate from here to here? So these are all interesting problems that we face today. Okay, so hopefully this gives you some context for our study of high frequency circuits. We study the frequency response because ultimately we want to design circuits for high speeds, high frequencies. All right, so let's go to today's lecture, and we're going to talk about the common base and common gate stages. So, frequency response of common base and common gate stages. Okay, I refresh your memory from Electronics 1 why the common base or common gate stage is interesting and useful, right? So if you remember, if you look at the very basic structure that we have here, this is some sort of bias. The input goes here, and the output comes out of here, and there's a load resistance. We said that in this amplifier, the input impedance is not low, is not high. In fact, it is low. So if you remember, if we look into the emitter of a bipolar transistor with its base at AC ground, of course the device is in forward active region, properly biased and everything. This input resistance is 1 over GM if we neglect the early effect. And this is a pretty low value. So for example, if the bias current is 1 milliampere, 1 over GM is about 26 ohms, right? And the reason this is interesting is that in some applications, we would like to have a low input impedance. What I showed you in Electronics 1 was that we have an antenna, a 50 ohm antenna, that needs to be properly matched, properly terminated, and we connected it to the emitter of a common base stage, right? That was the idea. All right, so now we know that this has some applications, and similarly the common gate stage. Now our objective is to understand its frequency response. Okay, so what we'll do is to keep it general. We will also add a resistor here. We'll call this RE. The purpose of this resistor is just let me just clean this up, just to make sure that we have considered, for example, the output resistance of the preceding stage, or interestingly, in some cases, we deliberately might add this resistance. Okay? I said that in the common emitter stage, we do not deliberately add the resistance in series with the input, with the base. But here, in some cases, we do, because it turns out that this resistor provides emitter degeneration, and emitter degeneration provides higher linearity for the circuit. So that's beyond the scope of this course, it's okay, but sometimes this resistor is actually added deliberately, not just modeling something before it. Okay, all right, so similarly for the common gate stage, we have a situation like this. So let's add a resistor here, RS. This is again a bias value. Of course, we do need a bias path here to ground, a current source or resistor or something. So we're not showing that. And then there is the output. All right, so remember the procedure I showed you before for computing the frequency response. The first one was to draw the circuit. We did. The second one was to draw all the capacitors of the transistors. So we go ahead and identify all the capacitances that we have. Let's go do that. So let's change the color of this pen to blue. All right, so the bipolar transistor has C pi between the base and the emitter. So that's C pi. Then it has C mu between the base and the collector, C mu. And then it has a capacitance from the collector to the substrate to ground. So that's a capacitance from here to ground, which we called CCS. All right, okay. How about the MOSFET? Well, it was a similar situation. We have CCGS, CGS, so that's the gate source capacitance. There's a gate drain capacitance, so that's CGD. And there are two caps from the source and the drain to the substrate, to ground. So there's one from this source to ground, we call it CSB, and there's one from the drain to ground, which we call CDB. All right, so that's the second step in our analysis. In the third step, we said, see if any of the capacitors can be removed or merged to simplify the circuit. All right, so we go and look at these circuits and see what happens. C-pi goes from the emitter to AC ground. But it doesn't merge with anything else. There's no other capacitance that goes from the emitter to AC ground. Okay, no problem. So we'll just keep it like that. I'm going to draw the circuit again, and this time again in red. So here's what we have. We have V in, then we have RE, and then we have this. This is AC ground, so let's just show it as such. And we would like to, again for the MOSFET as well, I can do the same thing. So V in, RS, AC ground, and let's go and drop all the capacitors in, right? So this is RC, this is RD, this is RD. Okay, so I will go back to my color of blue for the caps. C-pi goes from the emitter to AC ground. So C-pi goes to AC ground. Okay, C-mu goes from the collector to AC ground. So that goes from the collector to AC ground. So we call that C-mu. And CCS also goes from collector to AC ground. So why don't we just add these two together, because they are parallel anyway, right? We went through this exercise before, after we defined or identified the high frequency model of the bipolar device, right? So okay, so that's what we have. We have really two capacitors, one connected in the input signal path, one connected in the output signal path. And if you remember, we also asked ourselves, is there Miller effect in the common base stage? And the answer was no, because we don't have any capacitance going from the input to the output. So there's no Miller capacitance, right? So this is the important result. So no Miller multiplication, no Miller effect. Either here or here, right? There's no Miller effect. Okay, so how about the caps in the common gate stage? Well, we have CSB from here to ground, great. How about this one? CGS goes from here to AC ground. So these two are in parallel, very good, so we just add them together. So we have CSB plus CGS. All right. Let's go to the output node. I have CGD to AC ground and then CDB to AC ground. So again, they add up. So we'll put that here. And we call it CDB plus CGD. So that's beautiful. You can see that the two circuits now look very similar. And the equations would be also very similar. What's also interesting and nice about this is that because there's no Miller effect, because there's no capacitance from one node in the signal path to another node in the signal path, I can readily find the poles by inspection. I can go to a node and say, how much resistance do I see at this node to AC ground? How much capacitance do I see at this node to AC ground? Multiply them, invert the result, that's the pole frequency, right? So then things are much simpler. All right, so let's do that. Let's go ahead and so we say find the poles by inspection. So I hope you remember this from several lectures ago, how we do this, right? Okay, so we start from the input and we come here. This node is in the signal path, the signal is going through it, and to find the R and C, essentially the time constant at this node, what I have to do is set all independent sources to 0. So I set this to 0, so that becomes a short circuit. And I sit here and I say, how much capacitance do I have to AC ground? Okay, so let's write that out. Cap to AC ground. Okay, C pi, right? We don't have anything else. So that's good. How about resistance? So resistance to AC ground. All right, so I sit here and I would like to find the total resistance from this node to AC ground. Looking to the left, I see RE. Okay, so I got RE. But is that all? How about looking to the right? Looking to the right, what do I see? Looking to the right, I see 1 over GM, right? Because I'm looking to the emitter of a bipolar transistor with its base at AC ground. So looking to the right, I see 1 over GM. So from here, this way to AC ground, I see 1 over GM. This way to AC ground, I see RE. So they go in parallel. So RE in parallel with 1 over GM. Okay, so we found the capacitance, the resistance, we just multiply them, we get the result. So we will maybe call that the input pole because it is in the input signal path. So we say omega P in is equal to 1 over the capacitance and the resistance, right? So RE over 1 over GM times C pi. That's it. You see, it was very simple, right? So long as we have that notion of associating a pole to every node in the signal path, it's pretty easy, right? We don't even need to draw the small signal model and write KVLs and KCLs. Okay, so that is the input pole. Let's go and look at the output node. So at this output node, I have some resistance and some capacitance to AC ground. Okay, so how much resistance do I have here? Looking from this way to AC ground, I see RC, so that's good. Looking this way, if I neglect early effect, I see infinity, so that's fine. All right, so that was for input. Let's go to the output. So cap is just that cap, CS plus C mu, CCS plus C mu, and the resistance is just RC. So resistance is just RC. So we can say that the output pole, omega P out, is just 1 over RC times CS plus C mu. Okay, so these are the two interesting results that we have found for the common base stage. All right, so you can see that there's also simple, if we have numerical values, we can quickly determine which one is at a higher frequency, which one is at a lower frequency. Typically, this output pole turns out to be at a lower frequency than the input pole. So that's something that can happen, but it just depends on the values. All right. You can see that extending these results to the common gate stage is very straightforward. So let's do that. So we say for the CG stage, we have omega in, omega P in. The input pole is given by this capacitance times the resistance we see at this node, which is again Rs in parallel with 1 over Gm. So 1 over Rs in parallel with 1 over Gm times the total capacitance that we have at the input, so CSB plus CGS. Okay, that's the input pole of the common gate stage. And similarly at the output, we have omega P out equals 1 over RD, total resistance times the capacitance, so CGD plus CDB. And that is these are the two poles of the common gate stage. Okay, so we see that we are gradually becoming more efficient at writing out the poles and hence quickly finding the frequency response. We are getting better at looking at a circuit and say, okay, there's a pole here, there's a pole here. Roughly speaking, that pole is given by these, this pole is given by these, so that we can quickly estimate the performance of a circuit, right? That's the essential component that we need to become good engineers and good designers, right? We can always write equations, we can always run simulations, but as long as we don't have the intuitive understanding of what the circuit is doing, as long as we cannot find these approximate values quickly, we will be handicapped. We will not be able to really perform good design. Okay, all right, so that was a quick look at these. Let's see. All right, I wanted to go over an example. So here's an example. I will build a common gate stage with a current source as the load. So here's the common gate stage. V in, Rs. This goes to a bias VB1. Let's call this M1. And instead of the resistor here, I would like to have a higher gain maybe. So I'm replacing the resistor with a current source. Okay, so here's a current source. This is properly biased by a current mirror here, right? And now we can call this M2, and this is the output node. All right, so let's go ahead and find the poles of the circuit. If we have the poles, then we can quickly plot the frequency response. All right, so the first step is to draw the circuit. We did. The second step is to drop in all of the capacitors of the transistors. So let's go ahead and do that. I will change the color of my pen to maybe this color. Okay. So for M1, we have CGS1. So CGS1. And then CGD1. CGD1. And then we have two caps from the source and the drain to ground. So there's one here, CSB1, and then we have one here, CDB1. So these are the four caps of the transistor M1. We do the same thing for M2. So M2 has a CGS. So CGS is from here to here, CGS2. Then it has CGD. So that's from here to here, CGD2. This got a little messed up. Let me clean it up here. So this is CGD2. CGD2. GD2. Okay, and then we got two caps from the drain and the source to AC ground. So here's one cap, C drain bulk 2, and then we have one more, source bulk 2. So source bulk CSV2. All right, so with all the caps in there. All right, so that's the second step. The third step is to look and see which capacitances can be removed or can be merged to simplify the circuit. All right, no problem. So we're going to start, look through them one by one and see what we can do. So let's just do this like so. Now we're going to start from the input. Do we have caps that can be merged? Sure, these two are in parallel. So these two will give us CSB1 plus CGS1. No problem there. All right, let's go to the output node and see what capacitances we see from there to AC ground. We have from here to this AC ground, CGD1. Then we have CDB1. Then we have CDB2. Then we have CGD1 also, right? This also goes to AC ground. So all these four caps become one. So I just put a little cross here, a little cross here, a little cross here, a little cross here. And I will say that all of these give us CDB1 plus CGD1, this, and then this and that, plus CDB2 plus CGD2. All right. Okay, so we got two more capacitors left, this guy and this guy. So what do we do with these? CGS2 goes from AC ground to VDD, AC ground. So it doesn't do anything, right? It's shorted out. So that's gone. And then CSB2 goes from AC ground to AC ground. So that's also gone. So that's very nice, right? So the circuit suddenly becomes much simpler. Okay, so let's redraw the circuit with all these eliminations and combinations taken into account. All right, so here's what we have. We got V in, RS, then we have a cap at the input to ground, which is just the sum of these two. So we have CSB1 plus CGS1. Then we got the transistor itself, M1, with the gate at AC ground. Then we got M2 sitting here with the gate at AC ground. This is M2. And then we have all these four capacitances that we added together in this form as the capacitance at the output node. So maybe I'll draw it this way. It's really the same thing, right? I draw it here, and I say V out is here. Right, this cap goes from output to ground, and its value is this whole thing. So I will write CDB1 plus CGD1 plus CDB2 plus CGD2. Okay, CGD2. And that's the circuit. So we have only one capacitance at the input, one capacitance at the output. It's great. It's easy to solve. All right, no problem. So as usual, in the next step, we will try to see if we can use, we can find the poles by inspection. All right, so is that possible? Well, let's see. At this node, I have some capacitance to ground and some resistance to ground. So that should be easy, like the previous example. Like this example here, right? We don't have Miller multiplication in the circuit, so things are much easier. Okay, so let's write out our input pole. Omega P in is similar to this case, right? CSP, CGS, RS in parallel with 1 over GM. So this equation applies exactly here, right? The same thing. So we have 1 over the total resistance that we see at this node is RS looking to the left to AC ground, and 1 over GM looking to the right if we neglect channel length modulation. So it's RS in parallel 1 over GM multiplied by CSB1 plus CGS1. All right, so that's simple enough. Okay, that's great. Let's move on to the output node and see what we should do there. All right, so as usual, I'm looking for the resistance at the node and the capacitance of the node to AC ground so that I can form the pole frequency. The capacitance is straightforward. We got these 4 caps that added to each other, so that's that. How about the resistance? What is the resistance that we see from the output node to AC ground? All right, okay, so let's consider for simplicity the case where channel length modulation is neglected. Okay, all right, so I'm going to write these here so that we can keep track of things. Okay, so case 1, lambda is 0. Lambda is 0 means there is no channel length modulation. So the output resistance of each transistor is infinite. All right, okay, so then what do we do here? Do we have a problem? We sort of have a problem, right? Because the capacitance is given, the resistance is infinite. So then where's the pole frequency? The pole frequency would be 1 divided by infinite resistance times capacitance. So the pole would be at 0 frequency. Is that a meaningful thing? In some cases it is meaningful. A pole at the 0 frequency corresponds to an integrator, right? An ideal integrator is 1 over S. But don't worry about that. In our case, it doesn't really make a lot of sense. So we will need to consider some imperfection of the circuit. So in other words, we should really think about case number 2. So case number 1, omega P out goes towards 0 because R goes to infinity, and we will not pursue that. That's not particularly interesting and not particularly relevant to the actual behavior of the circuit. So we go to case number 2 and we say lambda is not 0, right? So there is some finite channel length modulation, and we should take that into account. We should take into account that these transistors have a finite output resistance. All right. Okay, so now let's go ahead and just draw that resistance in here and see what happens. Let me change the color of the pen to maybe this color. Okay, so we have RO1 here between the drain and source of M1, and then we have RO2 here between the drain and the source of M2. Okay, all right, so then I'm trying to find the resistance that I see if I sit at the output node and look in all directions to AC ground. All right, let's sit here and look up. What we see is RO2 to AC ground. That's great, so we have RO2. But then what happens if I sit here and look down? Do I see RO1? No, because this is not AC ground, right? This goes to RS. So how much is this resistance if this source is not AC grounded? That should look familiar, doesn't it? Okay, so let's go to the next page and see. In fact, I can just go scroll up a little bit here to keep everything. Okay, so let me redraw this part of the circuit so that you can see. I redraw the circuit. Here's M1, right? Here's resistance RO2. So far so good, right? let me just draw this vertically, RS. And remember, when we are finding poles by inspection, we set all independent sources to 0. So that's why this V is set to 0. Okay, so do I know the resistance looking down here? I do. This is a MOSFET that has source degeneration, and we know the equation for that output resistance from Electronics1. So if I call this R out 1, meaning R out of M1, then we remember that that's given by 1 over GM1, 1 plus GM1 R01, the intrinsic gain of the transistor, times the degeneration resistance plus R01, right? We know that. Okay, so then when I sit here, I see two resistances in parallel. This one going to AC ground is R02. This one going to AC ground is this. So both of these go in parallel, and that's the net resistance that we have at the output node. We take that net resistance, multiply it by this whole capacitance, that is the output pole. So we say omega P out is equal to, I have to write a giant fraction here, the resistance. So RO2 in parallel with this whole thing, which came out to be this, right, this output resistance. So it should be lowercase. So RO2 in parallel with this whole expression. So 1 plus GM1 RO1 RS plus RO1. So we got the resistance, right? Resistance looking up is RO2. Resistance looking down is that of a degenerated transistor. Is this, so that's the resistance. This resistance is multiplied by the total capacitance that we see from the output node to AC ground. So I have to put another set of brackets here and then multiply that by these caps. So CDB1 plus CGD1 plus CDB2 plus CGD2. That is the output pole frequency of this circuit. Okay, so that's an interesting exercise in bringing everything that we have learned together, right? Now we can drop in the capacitors, we can try to find the poles by inspection. If we arrive at some sort of structure whose resistance is not straightforward, like this, we can go back to what we know from previous experience in Electronics1 and Electronics2 and readily write these out. All right? Okay. All right, so there's one little note that I would like to make sure that is clear, and that is this. When I'm calculating this output resistance, R out 1, looking down here, I drew the circuit like this, and I found the resistance, right? Okay, but in reality, it's not like this, right? In reality, there is one more component that I sort of just swept under the rug and didn't talk about. There is a capacitance here, right? Remember this capacitance? So there's a capacitance equal to CSB1 plus CGS1. So I can't really say that looking down here, I see this, right? Because this capacitance is now in parallel with RS. So what we see here is a general impedance. It's a complex impedance. It's not just some resistance, right? So yes, so there's an approximation in what we're doing here. So when we say that the output pole frequency is given by 1 over this resistance times that capacitance, Yes, it's not quite correct because it's not a pure resistance that we find here. And this happens in this particular case because this resistor creates interaction between this node and that node, right? If I didn't have this resistance, everything would be fine. We have some pure resistance here, some pure capacitance here. For the output node, everything is good, right? But now we don't. So yes, there is some approximation here. In fact, if we go back a little more, you can see that there's one more approximation that we haven't talked about. Let me show you. So remember that we said looking into the source, we see 1 over GM here or here, right? But that's true only if there is no channel length modulation. If there is channel length modulation, what we see here is not 1 over GM. It's more complicated and we have not talked about it. So even for the input pole frequency, we have an approximation because when I wrote the input pole frequency, I assumed that at this node I see RS looking this way and 1 over GM looking that way. But that's not true because if I sit here and look this way and RO1 is there, what I see is not just 1 over GM, it's something more complicated. So that's okay, we're making these approximations, but the point is that we can readily find expressions for these pole frequencies and hence understand the frequency limitations of the circuit quickly before we jump into equations and simulations and so on. All right, very good. So this was our analysis of the common gate and common base stages. And what we saw was that, first of all, there was no Miller multiplication. And second, we could find the poles by inspection. And we see that there's a pole at the input, there's a pole at the output. In most cases, the pole at the output turns out to be the lower frequency one. So that's the one that limits the bandwidth. That's the one that would be sort of dominant. But of course, in practice, we just have to see the numbers. All right, this concludes the lecture today. I will see you next time.